about catastrophic plate tectonics, a global flood model for Earth history. And it's a progress report. And we have a catastrophic plate tectonics research group. A bunch of us have been thinking about this subject. I was the leader of the group, started the group. John Baumgardner, PhD in geophysics, was involved in our group. Russell Humphreys, a pure physicist with experience in earth magnetism, he was in our group. Andrew Snelling, a hard rock geologist, what we call an igneous and metamorphic petrologist, was in our group. And Larry Vardaman was in our group, a climatologist and meteorologist. And Dr. Kurt Wise, a paleontologist, was in our group. And we started meeting and talking about this issue of plate tectonics and catastrophic plate tectonics. And over the years, we have built a kind of position statement that we think should influence our thinking and other people's thinking. And if you look at the Earth, you see something remarkable about the Earth. We have two kinds of landforms on the Earth. We have continent, we have ocean floor. And so we should understand the continents and ocean floor. Do we have a projection pointer I can use? Do we have one of those handy? Anyway, I'll call your attention to most of the planet. About 70% of the planet is ocean floor. And the ocean floor is lower elevation, about 12,000 feet above sea level. And then the continents are expressed above sea level, about 2,000 feet above sea level. That's remarkable. Well, I'll talk about the tectonics of the Earth, the tectonic models, various tectonic models, especially because they go way back in the history of things. I'll talk to you about the pre-flood Earth. I'll talk about what was the physical cause of the global flood. Try to pose that question, ask it, and give some answers. And then I'll try to think about computer modeling plate tectonics. We believe it can be modeled in a catastrophic way. I'll talk to you about sediment transport mechanisms in the flood, a little bit about volcanoes and earthquakes, how the flood ended, the post-flood geologic process, the post-flood climate what we have today, and then a little bit draw some conclusions. Very good. Okay. So now I can, whoa, that's great. Okay. All right. So there we go. We got the overview. Okay. Tectonic models. You know, ancient literature, way back, deals with tectonics. Plato's Atlantis, okay. Lots of other things regarding ancient literature. The statements of Scripture regarding tectonics. The theory of Antonio Snyder. Remember Antonio Snyder? I explained last night, the author of Catastrophic Plate Tectonics in 1859. Modern theories of continental drift and plate tectonics. Antonio Snyder's theory of continental sprint was slowed down to make the modern theories of continental drift and plate tectonics. Well, ancient literature has a theme. The Gilgamesh epic and the Enuma Elish account in the Babylonian literature. Greek, even American Indian tribes have tectonic elements to them. What does Scripture say about the formation of continents and ocean basins? Genesis 1 verse 9 says, God said, let the waters below the heavens be gathered together in one place and let the dry land appear, and it was so. And then it goes on to say, in the gathering together of the oceans he called seas. Okay. All the fountains of the great deep were broken up in Genesis 7:11, a great tectonic event. The fountains of the great deep, and then were broken up. The Hebrew word is bekah. Bekah means to split open or cleave. And all the high hills under the whole heaven were covered. You notice that the flood begins on the ocean floor, evidently, with the fountains of the great deep being broken up, and then it proceeds to the high hills on the continents. All the high hills on the under the whole heaven were covered. And it's a Hebrew superlative. You cannot say it in a more concise way that the floodwaters covered everything. All the high hills under the whole heaven were covered. Antonio Snyder's map of the pre-flood Earth, the continents joined some way, and the idea that the continents split apart as a result of the flood. La Création et ses Mystères d'Evoluer, published by Antonio Snyder, 1859. Bad year for plate tectonics, especially catastrophic plate tectonics, and publishing the flood because the world didn't want to hear more catastrophic ways of thinking about the earth. They wanted to hear uniformitarian thinking. And of course, Darwin ascended to popularity about that time. It wasn't until about 1910 that Alfred Wegener dusted off Snyder's theory of catastrophic plate tectonics and put it in an evolutionary time scale involving millions of years. And then continental drift was ignored till 1963, right in there, and then seafloor evidence became available to suggest that the giant mountain range around the ocean basins was a result of a plate divergence, and seafloor spreading became recognized among geologists, and some of the elements of plate tectonics became very popular in the late 1960s. Well, what happened to the floor of the pre-flood ocean? That should be probably one of the primary questions that we should answer. Now, we don't have a lot of familiarity with the ocean floor directly, but we have all the geophysical data about the ocean floor. And as you look at the Pacific Basin, for example, on this image of the Earth, you can see that it's not just a ring of fire with volcanoes around it, it is a basin of fire. Okay, but because that ocean floor is full of tens of thousands of volcanoes on the ocean floor called seamounts and guyots. Maybe you've heard about those. And there are volcanoes around the Pacific Rim, yes, but the whole basin is volcanoes. And so the ocean floor is a volcanic feature dominated by volcanic rocks. The typical rock is called basalt, and it's erupted and the volcanoes erupt basaltic lavas on Hawaii, and that's the kind of rock that the bottom of the ocean floor is made out of. The ocean crust is thick, but not as thick as the continents, maybe 10 kilometers thick. The pre-flood Earth, let's talk about the pre-flood Earth, and I'll talk about the Earth's internal structure a little bit, about the granitic continental lithosphere, about the basaltic oceanic lithosphere, and here you see kind of the idea. The Earth's internal structure can be divided into three different elements: the crust, which is silicate rocks, typically of basalt or granite composition; the mantle rock, which is typically of a basaltic composition but is rock, not molten. The outer core of the Earth is molten, we believe. The inner core is solid. And so the majority of the Earth is mantle, the mantle of the Earth, and it's silicate rock. It's oxygen and silicon with magnesium and iron and other elements like that. Anyway, the mantle of the Earth is this material that behaves like a rock in earthquakes. We know about its properties indirectly, like from earthquakes. And we think we've found pieces of mantle that have been erupted and quenched, and that gives us some ideas about the mineral structure down there. But anyway, the crust is what we see, and the mantle is kind of largely concealed from us, but that's the major part of the Earth. And what we need to think about is the crust and the mantle of the Earth to understand catastrophic plate tectonics. So if you look at the Grand Canyon, you see underneath the Grand Canyon the crystalline rock in the basement. There you see the Colorado River, and you see the granite rocks down there, granitic rocks, Vishnu complex metamorphic rocks, and Zoroaster granite that make this rock that's the basement of the continents. And the basement of the continents is this kind of rock that's widespread through across through the North American continent. But all continents have this kind of rock as their dominant rock type. This rock type is very different from the ocean floor rock. Now, we have lots of feldspar and lots of quartz in this rock. Mineral quartz is most distinctive of the granite rocks of the continent. Ocean rocks have very little quartz. The mineral quartz, they have some feldspar, but they have more heavy minerals like hornblende and pyroxene, things like that. granites tend to have biotite mica, that type of thing. A little bit different chemistry and composition. Okay, well, granite in microscopic view, if you look at it, it's made out of three different characteristic minerals. Feldspar, which is the dominant mineral of the Earth's crust, quartz, which is a silicon dioxide mineral, and typically mica, or biotite, what's called iron mica. Those are typical granite. And because of those dominant minerals, and because feldspar and quartz are the dominant minerals of granite, this rock has a density of about 2.8 grams per cubic centimeter. Okay, 2.8 grams per cubic centimeter. In other words, it's 2.8 times the density of water. Okay, that's a good way to think about it. Okay, and basalt in microscopic view, you see something different. You see the texture is finer, less crystalline, because it's typically quenched by contact with water or cooled differently. You'll see some larger minerals in there. Those are some feldspars, and also see minerals that are iron magnesium minerals, such as pyroxene, and those kind of minerals. And because of the difference in composition, the basalt rock can be 3.2 to 3.0 grams per cubic centimeter. So the density of granite is about 0.5 gram per cubic centimeter less than the density of basalt. So basalt is higher density, about 3.2 grams per cubic centimeter, and the density of basalts are higher than for granite. Okay, why are there oceans? Okay, here's the brief explanation. You see the continental crust there is, the continental crust is thicker continental crust there, okay? And then the ocean crust is thin. And think about the difference in density between continent and ocean floor. The thicker continents, being lower density, cause them to rise, okay, higher, and they displace the root of the mantle below into the root mantle below. The ocean crust is thinner but higher density, and so it floats lower but is not as thick. And so it allows the freeboard of the continents over the ocean basins. And the principle is like balsa wood floats higher in water than oak wood, right? Oak is higher density, so it floats deeper. And so you think about that. The ocean crust, the oceanic crust, which is dominantly basalt, has higher density. It's thinner, so it floats lower on the mantle of the earth than the continental crust, which is lower density and thicker. So it creates the freeboard. So that's what I think it's like. And so the day before the flood, what does the earth look like? It has basaltic crust, ocean floor, like we have today, probably largely gone. It has the same continental mass or crust that we have today, just recycled. The day before Noah's flood, we had a similar configuration as we do today, basalt and granite, different continental distribution, but we had the same continental composition. So the ocean basins were probably created on day 3 of creation week with this different rock type. What was the physical cause of Noah's flood? Very good question. Internal and external and internal or supernatural causes. You might think about this. Could the flood have caused itself inside the earth, an internal cause? Or is there an external cause, like asteroid, him hitting the earth or something? Or is there a supernatural cause, God pushing a button, releasing some trigger or something? Anyway, that's something to think about, external or internal. Genesis 7 verse 11 talks about the fountains of the great deep being broken up. So it has a tectonic theme to it, doesn't it? It has the Hebrew word bekah, broken up or split open. And what are the effects of new hot ocean floor? Okay, new hot ocean floor was produced. And if plates were subducted, then we had new ocean floor formed. A new hot ocean floor may be different than that cooler pre-flood ocean floor. then we have spreading, subduction, and mantle-wide flow. Those are the processes that have to go on if plate tectonics is going to occur on an Earth that doesn't expand. In other words, a constant volume Earth. The initiation of the flood. Well, was it a supernatural mechanism, just the hand of God? Or God slamming the door on the ark or something like that? Or is it an astronomical cause, like a comet, meteorite, asteroid, planet near miss, something like that? Or is there something internal within the Earth, a terrestrial cause, like something lighting off radioactive decay and a heat buildup, or canopy collapse, or some other trigger? Well, the initiation of the flood is described in Genesis chapter 7, verse 11. The same day were all the fountains of the great deep broken up, and the windows of heaven were opened. That's the beginning of the flood. And it's a general seafloor upheaval, I believe, something there to it. The fountains of the great deep. Fountains is the Hebrew word mayin, which means water sources or springs of the great deep. Now, in the Hebrew, the word great deep is a stereotyped compound noun. There is no the in the original Hebrew. So fountains, great deep. And so the Hebrews had this very special significance that they attached to the great deep. And the great deep is obviously a big ocean, okay? And so this great deep is what they're referring to. So whatever the fountains of the great deep are, they were broken up, okay? And the windows of heaven were opened. Another cause of the flood was the windows of heaven and the unprecedented downpour of rain. Okay, so from the standpoint of Noah, he sees what? Looks out the window of the ark and he sees the windows of heaven are open. But the omniscient narrator that's giving us the text is telling us the fountains of the great deep is in there too. And it's mentioned first. So you see what I'm saying about that cause of the flood. So the origin of floodwaters, the situation before the flood, we had cold, dense ocean crust, and we had higher granite continents. Okay, so this cold, dense ocean floor is going to be replaced by what? Mantle rock that rises to form hot ocean floor of basaltic composition. You see what happens here? When you replace cold ocean floor with hot rock, what happens? It rises because hot crust is lower density than cold crust. If it's made out of the same material, mantle of the earth, it would be warm or hot. And that, what does that do naturally? It raises the floor of the ocean. And so we have internally within the earth a catastrophic mechanism to unload the continents, or unload the ocean floor, unload the ocean onto the continents. Okay, the principles of plate tectonics are three. We have spreading, we have subduction, and we have mantle-wide flow. Spreading, where two plates pull apart, okay, what happens? It creates a gap, and in that gap, mantle rock, plastic rock, can rise, and as it rises into that crack, it melts and then recrystallizes, and that forms a new ocean floor. And as ocean floor spreads or moves apart, you form a new rock in the crack. Okay, and then we have subduction, where mantle rock is receiving crust. As the crust falls, then it creates subduction, and then the mantle is deformed, and you see mantle-wide flow. Plastic deformation can occur to rock on a large scale very rapidly. And this is what's been modeled in some of these experiments. Spreading, subduction, and mantle-wide flow. It happens in the mantle. Subduction is a process where the gap forms. Mantle-wide flow, all those arrows indicating the plastic deformation of the mantle. And then spreading. Okay, so subduction, we have spreading, we have mantle-wide flow. Okay, computer modeling of this catastrophic plate tectonics has been done on supercomputers, and it's done in 3 dimensions by modeling the mantle of the Earth. This was done with Los Alamos supercomputers and a code called Terra Computational Mesh. And the mantle of the Earth can be simulated, what's called finite element analysis, using a computer by breaking the Earth into a series of layers, you see here the layers. And those layers have, they're stacked up on top of one another. Each of those little icosahedron layers, you see, looks like the ceiling of a planetarium, the planetarium ceiling. You know, the geometry of that special geometry is used to simulate the mantle of the Earth, and then we can do deformation experiments on it. And anyway, over this mantle 3D mesh, you can lay the continents, and you could subduct the ocean floor, and so that's what's been done with this, and millions of hundreds of thousands of these little elements or cells of the mesh can be deformed. This is one of the experiments. It shows the continental configuration such as you see here. See North America, Africa, South America, Antarctica, India, see Australia, and then you see Europe, Asia over here, Greenland, okay, and you have Tethys, this pie-shaped thing here. That's the initial configuration in this particular run. Whether that was the pre-flood configuration, I'm not so sure that's the right configuration. But in this deformation experiment, we caused the mantle, or we caused the ocean floor to unzip or deconnect from the continent around the western part, the eastern part of the Pacific Basin, and around the western part of the Pacific Basin and along here. And you see what happens. And when you tip this ocean floor, we believe it was cold. It's of the same composition of the pre-flood mantle of the Earth. What would happen? It could sink. In other words, we are modeling the deformation of the Earth, assuming that the pre-flood ocean floor was the same composition as the pre-flood mantle, just cooler. And the difference in temperature creates higher density of the ocean floor, and the ocean floor is able to be subducted and sink. Like an aircraft carrier can sink in the ocean, metal is higher density, it sinks. And so ocean floor could sink into the mantle. And we, in this numerical experiment, it's detached along the margin of that supercontinent. In cross-section, you can see what's happening. You can see spreading occurring here. You see the cold ocean floor falling into the mantle of the Earth. And it's creating mantle-wide flow. And you see those little vectors showing you which way the mantle-wide flow is going. So spreading, okay, subduction, mantle-wide flow. Here it is. This is 40 days into the event. You see plates have descended almost over halfway through the mantle of the Earth. Okay, 1,000 kilometers thickness, so that's fallen quite a distance. And you see over here it's fallen, and then the mantle-wide flow. The velocity of this deformation as it accelerates goes up to about the maximum of 2 meters per second. In other words, these plates, we think, can fall about 2 meters per second into the mantle. The mantle is rock, and as the plates fall, there's a liquid area around the plate as it descends, and that low viscosity melted rock allows the plate to accelerate to about 2 meters per second, a meter per second, as it falls into the mantle of the Earth. Here at 60 days, you see what happens. There are crust, there's ocean crust that's fallen all the way to the core mantle boundary. The core of the Earth is higher density material. We think it's some kind of alloy of iron and sulfur or something like that. That doesn't allow the silicate rock to penetrate. And so the bottom of the mantle contains a large lithospheric junkyard of the pre-flood ocean floor. And you see what's spread out there after 60 days. Whoops. And here you see modeling the Earth. You can see the continent expressed. The topography is there. Okay, what happens? The continent is depressed around the edge, and then water invades, And you see the purple line is telling you where the ocean actually invades. As this subduction occurs along the eastern side of the Pacific basin, as that's subducted under the North American and South American continents, what happens? The continent is depressed and water enters into the goes into the center of the continent. And of course the hot rock is formed in the crack between the supercontinent as it opens, and what do we see in there? That's probably the fountains of the Great Deep. Here it is at 60 days into the deformation experiment, and you can see a significant part of the Atlantic Basin has been formed as the supercontinent breaks apart. And the Indian Ocean Basin is forming. And the vectors show, here's a vector view showing you the velocities that are attained. The maximum velocity here at about 60 days on the surface is about 1 meter per second. That's the maximum velocity. If you think of Africa staying put, you can measure the velocities relative to other things. A polar view, you can see looking down on the Arctic Ocean as it's forming from the plates diverging. Again, meter per second water maximum velocity. And this is view from the South Pole. You're looking at Antarctica there. Okay, and here is the surrounding Antarctica. There's all that spreading going on. And we're looking at there's South America, there's Africa, as the Atlantic Basin is forming. And then a large part of the Pacific Plate pre-flood is being swallowed up. If you take an Earth, a globe, and hold it, you can see something very interesting. The ring of fire goes around the equator of the Earth if you hold it that way, with Africa on the North Pole and the South Pacific Basin on the South Pole, North Pole being Africa, South Pole. If you hold it like that, the Pacific Basin or the ring of fire goes around the Earth like an equator. And so that shows you something of the spherical geometry of how this plate subduction occurred on that kind of Earth. And so you can actually see that it is a straight line, okay, across. And there's the Cordilleran deformation belt all the way through western North America into South America. The Pacific Plate is moving this way. The North American plate is moving away from Africa south, and the resultant vector is like this. And so along California, we have strike-slip faulting. We had a little bit of plate subduction due to a plate boundary in here under Washington, but the primary motion of the North American plate and the Pacific plate creates this resultant that we have a head-on collision in Alaska. Head-on collision of Pacific plate with Alaska. So you look at Alaska and you see the head-on collision place. You look down in western the 48 states, and you'll see Washington, Oregon, California with this oblique collision, largely oblique collision. And so the great mountains in the southern part of Alaska, that would be Wrangell, St. Elias, Chugach Range, Kodiak Island, all of that is related to this head-on collision. And so I love going to Alaska to see the head-on collision because of places like that. And here's the, there is Bagley Ice Field. There's the mountains, the Wrangell, St. Elias Range. Here's the Chugach Range. These mountains in Alaska are the features from the head-on collision. The Andes Mountains the same way. So I love thinking and going to Alaska, doing that kind of thing. Okay, sediment transport with plate subduction occurring, right? Plate subduction occurring against a continent. What happens? A conveyor belt moves sediment from the ocean floor where? To the edge of the continent. It doesn't want to be subducted because it's low density. Clay minerals and quartz and things like that are lower density. They don't want to go down with the plate. The cold plate can be subducted, but the sediment on the cold plate doesn't want to be subducted because it's low density. So we have a conveyor belt that moves sediment to the edge of continents. And then what is happening? We have tides and we have huge waves generated by the earthquake activity of the tectonics. So imagine a magnitude 8 or 9 earthquake here in western Washington due to plate subduction, and then imagine a continuous line of magnitude 8 or 9 earthquakes continuously for a year's period of time. Okay, that's the kind of thing you need to imagine if plate subduction is happening rapidly like we propose. Large rocks are found in the bottom of Grand Canyon, big boulders like this 200-ton boulder, 20 feet in diameter, very, very abundant. In the Kingston Range in Southern California, we have large blocks or mountain pieces that have slid. And in this illustration, I'm showing you a kilometer in thickness slab of rock which slid horizontally over the surface of the earth in a layer full of other broken pieces. This, I believe, is the beginning of the flood in the Mojave Desert. The Kingston Peak Formation contains the early flood deposits in the area. And okay, not only do you see large gravity collapse features like the big boulder deposits, but we see supercurrents. And evidence of flowing water creates supercurrents. And these sandstone layers, like at Zion National Park, have this diagonally tilted layers called cross-bedding. And cross-bedding is a primary feature of many sandstone bodies, provide evidence of deep water, fast-moving current. Not wind deposits. This is not a dune. This is deposited by water. We have water going over the continent at about 1 meter per second. That's what the stable velocity for forming large underwater dunes. And these are called sand waves. They've been seen on smaller scale in tidal estuaries in the Golden Gate in San Francisco, the place, but they're over widespread areas. And so continent. And there's a person there for scale. See the person right there for scale? So you get some idea. These dunes are huge in the sand bodies and provide evidence of fast-moving water, about 1 meter per second water velocity, which is consistent with that meter per second plate velocity. And over the North American continent, we have a buried sandstone layer called the Sauk sequence. And there's a Cambrian sandstone that's in the Grand Canyon and in southwest and eastern California that goes all the way up into North Greenland and around through middle part of the United States into Newfoundland area. And it goes over, if you assemble Europe against it, it's in Scandinavia. And around the Canadian Shield is this giant blanket of sand. Could that be associated with the onset of the flood? As we look around, we see evidence of current in volcanic ash deposits like the Painted Desert in Arizona. Petrified Forest National Park should be called Petrified Logjam National Park. You can see the very beautifully agatized logs that are there. Cell structure of wood, bark sometimes on or peeled off, roots and branches removed. Obviously, these things have been floated. And so a great stranded mass of ripped loose logs. And coal beds are what? They're floating mats, aren't they? They've formed from floating mats. And that's been floated around and redeposited. And then so coal is interlayered with marine rocks. So it looks like a marine flood was over Illinois in this case. And of course we have the dinosaur deposits like there at Dinosaur National Monument. 1,500 bones on the quarry face, the quarry sandstone. And you see the way dinosaurs were buried in some type of slurry flow, like and very high sediment concentration flow. Not a normal river deposit that buried these dinosaurs. And in Texas, we see here a 3-foot thick layer of what? Clams, clam fossils dominantly. Whole clams. Okay, how did whole clams get buried? The muscles and ligaments were holding the shell shut. You know, when clams die on the beach, they fall apart. The hinging ligament pops the shell open, natural tendency. When the muscles are in there that holds the valves two valves of the clam shut. So rapid burial, I see that all around us. Volcanism and earthquakes. Let's talk about how magnetism is preserved. When a rock cools from a molten condition, lava flow cools, at the moment it crystallizes at a certain temperature, it records the magnetic field of the Earth. We have a lot of reversely magnetized rocks and normally magnetized rocks, and it appears that the Earth's magnetic field has flipped during Noah's flood. And this idea has led us to understand that large masses of seafloor are reversely magnetized, and this magnetism was imprinted rapidly. Like on Steen's Mountain, one lava flow has two different directions. And that indicates that the Earth's magnetic field within a week or so can reverse. And so a loop of magnetic flux probably created at the core mantle boundary can transit through the mantle of the Earth to the crust and be imprinted in lava flows. And so probably plate subduction is one of the processes that initiated the reversal of the Earth's magnetic field. And around this Pacific Basin, we have the Ring of Fire, the Pacific Basin, but it's really the basin of fire, isn't it? We have all of these earthquakes and all of volcanoes. Anyway, you can see where the modern earthquakes are. They're in belts around the basin, and that's where the plate subduction occurred. And so we're seeing the residual effects of the ancient plate subduction. Okay, let's talk about the termination of the flood. The statements of Scripture, the accommodation space made for the ocean, the beveled surfaces of the continents. And the waters retreated from the earth, going and retreating, and the waters were going and falling until the 10th month, a literal rendition of Genesis 8:3 and Genesis 8:5. Well, the flood of described in the Bible, the waters were coming and going, or going and retreating. So it's an oscillatory motion, it seems like. And the waters were coming and going until the 10th month. So the middle of the flood, at the end of 5 months, this unusual 6 months, the end of 6 months, this unusual going and retreating is happening until the 10th month. So it's there's a large amount of that. And when you look at the surface of the Colorado Plateau, you can see it's beveled off. And the beveling of the retreat of the waters of the flood seems obvious. To me, the canyon was formed in the post-flood period. The retreat of the floodwaters was generally over a sheet-like area, and so it beveled off the top of the plateau. Okay, so post-flood geologic process. We have tectonics, we have volcanism, we have sedimentation, we have erosion, global cooling. And the post-flood world cooled, and the intensity of geologic process declined. And the raininess of the post-flood world declined to the present arid Earth. And then we had an ice age. So a lot of things are happening in the post-flood world. So exponential decline of process in the post-flood world from the very high, very potent geologic processes that were initiated by the flood and the catastrophic process during the flood year, and that's largely in exponential decline in the post-flood period. So when Noah got out of the ark, there was a rainbow, but it wasn't just happy business like normal. There was a world that was still in significant geologic change. And I don't blame them for wanting to stick around at the Tower of Babel rather than go out over so large areas of the earth, because there were still a lot of things happening out there. Well, in the post-flood world, lots of things were happening. Think about this. Those plates that were subducted under the continents stopped subducting or slowed very much to the present. And then things rose and fell, subsidence and uplift, loading and unloading, and so the vertical tectonics and isostasy, that's the principle of equal pressure with depth, allowed certain parts of the continent to sink and other parts to rise. Ocean floor was hot, right? And what happens when hot ocean floor cools? It becomes higher density and sinks. And so in the post-flood period, the cooling ocean floor, as it cools, it sinks. And so what happens? The continents appear to rise relative to the ocean. And so in the post-flood period, it looks like the continents are emerging out of the ocean. And that's what we indicate and see. We see these giant folded rock strata layers. Here's some people for scale. If you look at the base of that cliff, you can see the people down there. Okay, and sandstone is twisted like taffy. This is the rise of the upwarp in northern Arizona called the Kaibab upwarp. And the upwarp occurred in the late flood, so-called laramide orogeny, and this created the monocline called the East Kaibab upwarp, and that feature created the blockage that allowed water to pond behind it and allowed a big lake to build up. And that lake was later breached, its dam, and became Grand Canyon. Lots of volcanic features to talk about. Shield volcanoes and composite cone volcanoes like Mount Rainier, Mount Baker, Mount St. Helens, Mount Adams. Down in Oregon, we have Mount Hood. Okay, cinder cone volcanoes, lots of lava flows, things like that. Calderas like Crater Lake. And so magma, especially magmas here in the under the western United States, are expressing themselves late in the flood and in the post-flood period. Large plutons of granite, like in the Andes Mountains, have cooled. We see out in eastern Oregon, like in the John Day country, great masses of volcanic ash, John Day Formation, Clarno Formation, overlain by the Columbia River basalts. And so giant flood basalts in the post-flood, early post-flood period, just oozing out, and large linear fracture systems. And the buildup of deltas, like this is the Nile River Delta. And the Mississippi River Delta, that's been prospected for oil, and it's a deep delta. Many miles in thickness of sediment has been accumulated there in the post-flood period. And a canyon erosion, like a Palouse River Gorge here in Washington State, 400 feet deep, several hundred feet wide, 6 miles long, gouged out by what? The great glacial flood from the broken ice dam there in Missoula, Montana, Lake Missoula flood. And the Cordilleran area in Idaho, that was a great ice dam there that broke. And Grand Canyon was breached by the lake, or series of lakes that were there on the Colorado Plateau. So you can imagine various lakes on the Colorado Plateau. The dam through the Kaibab upwarp in northern Arizona failed, and this lake drained, creating a canyon. And then more lakes up here. That Canyonlands Lake failed, and other lakes failed. And so the falling like dominoes of lakes created canyons like Grand Canyon. Post-flood climate. It was a hot ocean in the Arctic, okay? So there's evidence of exponential cooling of the oceans. There's increased rain and snow just after the flood because of the hot oceans, and that's the cooled oceans now created the onset of glaciation. And then we live in an arid Earth. We have big deserts on the Earth today, and we live in the present Earth. And so the Earth has cooled, and there's global cooling on a global scale indicated by the seafloor data, for example, the oxygen isotope data of in the Arctic Ocean. And so there was a warmer ocean up there, and it's cooled off. So just in the thousands of years since the flood, the ocean has cooled, and it created this precipitation. And Dr. Larry Vardaman has modeled the raininess that occurs when you have a hot ocean. And the cooling Earth creates this ice age naturally. So what do you need to have an ice age? You need heat and you need cold. You need hot oceans and you need cooling, global cooling. And the cooling creates this ice age. And so precipitation allows the buildup. And you can see there's North America, and you can see lots of ice and glacier precipitation. So the whole global circulation pattern has changed during the ice age, and then following, we're living in the after effects of this global ice age. And the global ice age occurred, and now we have a little bit of global cooling, warming, and it left things like Yosemite Valley, beautiful valley, U-shaped valley, which was filled with glaciers. Now the glacier is largely absent just in the upper part of the drainage basin, but there was a huge glacier that was in Yosemite. And in many of the higher mountain areas here in Washington State. And then we have the distribution of animals after the flood, the distribution of animals, and like the elk, right? The elk in the blast zone are amazing. Think about those elk. We thought that they were a forest-dwelling animal, that they would have problem in the blast zone of Mount St. Helens because they have that thick hide. What are they going to do in the summer when they can't find shade? They're going to die of heat exhaustion. But what happens? They found that there's a cooling behavior. Elk like to cool themselves in wet soil, and they go in to take a siesta, and they do fine. In fact, more elk in the blast zone, I think, than in the surrounding forests at Mount St. Helens. So elk are amazingly versatile animals, and so we imagine all kinds of animals distributing widely in the post-flood period. And then, of course, the earth became more arid. Okay, the raininess declined, and now we have great deserts like the Sahara Desert. But the Sahara Desert was once a lake. There's lake sediments underneath the sand of the Sahara. And great river valleys were opened, and drainage of lakes created canyons. There's the earth, the post-flood earth. Distribution of continents, present distribution of continents. Boy, there's a lot of things that plate tectonics explains, and in this complicated graphic, I can point to some things that catastrophic plate tectonics explains, and it has great explanatory power. And because of a global worldview involving the flood and plate tectonics, I like to think this way about the Earth, and so. I've integrated plate tectonics into my flood model, and I hope you can understand a little bit about what that's like. But earthquake focal mechanisms, earthquake distribution globally, these big faults, detachment faults especially that make up mountains, that fits nicely with my view of plate tectonics. The way the magnetism in rocks is, polar wandering, the magnetic striping of the ocean floor, the details of how it's imprinted on the rock, that's interesting. And lots of things dealing with the continent shape, fossil distribution, ocean geology, boy, the ridges of the ocean floor, the mantle velocity anomalies, especially on the seafloor, or pardon me, on the base of the mantle, that fits nicely with plate tectonics. Mineral phases in the earth, like to think that way. Plate tectonics just sits nicely. The temperature trends after the flood, ice age, and we need a mechanism for the ice age, having really hot oceans. Plate tectonic, catastrophic plate tectonics, that fits nicely. The distribution of continental rocks, and deposition of the sandstone layers makes sense. Thick and widespread deposits of especially sand and mud, of really distant locations. Flood basalts like here in Washington. Kimberlites or erupted diamond-bearing pipes from the mantle of the earth. Those things are catastrophic. The actual source and destiny of the floodwaters fits nicely with plate tectonics models. The source of the floodwaters is just the simple pre-flood earth, and the lifting of those ocean floor rocks by the replacement with new hot ocean floor rocks unleashed the ocean on the continent. And it's a rather simple explanation to get rid of the floodwaters from off of the earth. Just have that ocean floor, new ocean floor form cool, and it changes its density. There's enough energy in the pre-flood ocean floor to be subducted. The gravitational potential energy of the cold ocean floor is about right to unleash the flood on the earth. Windows of heaven can be related to seafloor volcanism. The fountains of the great deep can be accommodated within this model. And things, other kind of things are all out there. So that's global tectonics and plate tectonics. Thank you.